the beams, which I will finish it, and then I have to show a generic inclined beam configuration today, and then we'll go for a MATLAB coding, which that code I already have presented in, I have completed the code. What I will do, I will share this code also at a later point with in the portal, Moodle portal. You can download it and then you can try it out yourself. So anyway, let's start today's class. So we want to the lecture 19. In the lecture 19, we were solving few examples. So in the lecture, I think we were looking for the case with a uniformly distributed load, and in the uniformly distributed load, we were kind of solving for the analytical solution as well as the one element solution. From the analytical solution, which I have derived at the end here, this is solution which I got it from the previous class. So or we can have it here. This is the exact solution which we are having it. So let me take this one. The exact solution this is the exact solution what we obtained from the previous class for the with a uniformly distributed load, that W of x is equals to a constant, and this is the this is the displacement, slope, bending moment, and the shear force diagram. So this is what we have got it from the exact solution. Similarly, from the finite element solution, this is one element Fe solution. So which is nothing but y tilde dy tilde by dx ei d square y tilde by dx square, which is nothing but bending moment ei dq. So these are all the finite element solutions. So if you look at here, this was fourth degree polynomial. This is third degree. This is quadratic. This is linear polynomial. Unlike our finite element solution, where y tilde is cubic, dy tilde by dx is quadratic, m of x is linear, and v of x is constant. So we can clearly see that we also demonstrated in the previous class that the exact solution at the nodal places will agree. So the D2, this thing obtained through uh, finite element is same as that we obtained through the analytical solution. So from this we can see that at the degrees of freedom, at the nodes, our degrees of freedom, which is nothing but y and dy by tilde, are same as y and dy by dx. But one can show that m tilde, which I call it as this one, which is ei d square y tilde by dx square, and shear force are not same as m and v. In fact, if I have to diagrammatically show, this would something look, it will look like this thing. Let me draw the picture. From the obtained solution, what we got, if I try to plot it, so displacement, which should be y, and let me just, because I'm drawing only in the negative part, so this is y with respect to x. If I have my exact solution to be this is fourth degree with this value equals to WL4 by 80i. So now let me just confirm it from the previous class. Okay. And the slope at this place at this place, I mean, I need to be very, so it has to satisfy the boundary condition at this place. That is, displacement is 0, slope is 0, something like this. But this is cubic, and it agrees the same thing. The tangent and the thing is same as the analytical solution. But this is the green is the 4th degree curve, and the red one is cubic. But they agree at this place, they agree at this place. Anyway, at the other node, we know y is equals to 0 and dy by dx is equals to 0. That's the reason you can see the tangent at this place is horizontal and the displacement is also 0. This is something like that. And similarly, if you just plot the other curves, you can see that the bending moment, if I draw the bending moment with respect to the analytical solution is a 2nd degree equation, the analytical solution will be something like this, with at the node B it is 0 and this is equals to WL square by 2. However, the FE solution for this problem would be something like this. It's a linear, so it's a straight line, something like this. So this is linear and FE solution, and this is so you can yourself can figure it out by seeing it here. So when if I substitute, anyway, this is a linear equation. When I substitute x is equals to L, this guy is not 0 at L. So that's the reason this doesn't match with 0 at this place. It is something different from 0. Whereas if you look at your analytical solution, so if I substitute L, this is 3, this is minus 3 plus 6, minus 3, it will go to 0. So that's the reason it is different. This is a thing. And similarly, if I plot my shear force diagram, so it's a linear thing for the analytical solution. And this guy is W into L. So, but even though the FE solution is not that good compared to analytical solution, but the same thing, if I look at how can I improve such a kind of solution? If I have more than one elements, then what happens is the same V of x, which has an analytical solution of this one, okay, anyway, I'll draw it here itself. If I have more than one elements, then let's say I have 5 elements. So if I have 5 elements, then I can have my shear force something like this. Each piecewise it is linear. Similarly, the shear force, similarly the bending moment, which is kind of a linear, can be constructed like this. Different lines. Different cubic for 5 pieces, a small cubic at every piecewise linear, which will fall closely compared to the analytical things. So that's the reason, even though a one element solution may be bad, but if you have many elements, that means piecewise linear, you can mimic very closely to that of the exact solution. Okay, in this case we have already know the exact solution, so that's the reason we could compare it. This is such that we can, just to demonstrate that even though finite element single element finite element solution looks not accurate, with more of such piecewise linear you can get very close approximation that matches with that of the analytical to certain tolerances. So that is what is the great thing about a finite element solution compared to analytical solution. In this case, we could derive an analytical solution, but not in all cases we would able to solve an analytical solution. Further, if you already know the analytical solution, why we need to even go for an alternate method? We already choose an alternate method because we could not solve our analytical solution mostly in the 2D and 3-dimensional cases where we have a complex geometry and a complex boundary conditions. So, but 1D is only to demonstrate that our finite element solution as close as possible to the exact solution. In some cases it falls exact, and some cases it may be not. So anyway, with this, the next topic I want to deal with it is the second topic of the day is when we have an inclined member. So the next topic is a beam element. Oriented arbitrarily. So that means if you have, this is your coordinate system, your beam, let's say the beam is oriented something like this. This is ith node, this is jth node, or simply 1 and 2. So then your degrees of freedom along this direction would be the locally, you, since it's a beam, tj, theta I and theta j. But we want in the global coordinate system. In the global coordinate system, we have, we can represent in global coordinate system d in the, for the I along along I, sorry, this is y direction, this along x direction, or let me just split it in here only. So this displacement can be have a components along di dix and diy. Similarly, this would have djx and djy along x and y directions. The rotation would remain same as theta because that would not be any problem. So we can show that, in fact, uh, which we also studied in our bar sections in the arbitrary rotations, we can show that dx dy in the local coordinate system is equals to cos sine minus sine cosine times dx dy measured in the global coordinate system. So in the local coordinate system, since this is a beam, in the so there is, since it's a beam, there is no axial here, whereas when it comes to the things, dx dy can have x and y, but it is not an axial thing unless this member behaves both as a bar and a beam, then only you have along the axial displacement also. So using this for a generic element, we can write neglecting actual displacements, let me see. This is a big zero. So this, we are only using this dy for this one. So that's the reason we only take minus sc dx dy, something from the global coordinate system. And because there is no dx, that is, since we ignored the global thing, that is because we don't have this axial moment. Since it's a beam, there is no longitudinal direction. If you haven't ignored this one, let's say if this behaves like a bar and a beam, then you will have a different things. So let me write it down for that. In that case, if it has both uh, this is, let's say, local, and this one is global, without ignoring the axial displacement. That is, it behaves like the member is both behaves like a bar and beam. In that case, then you will have d1x, d1y, v1, d2x, d2y, v2, c, yes, minus s, c. Earlier we had only these things, so this is same as this thing. Okay, these are same, so that's the reason we just took it. But now if you are assuming that axial displacements are also present, then we should able to try to take this thing into the consideration. So 0, 0, 0, 1, a big 0, that means 0, 0, 0, 0, 0, 0, 0, 0, 0, and a big 0 with d1x, d2y. v1, d1x, d1y, v1, d2x, d2y, v2 in the global, and this is your local coordinate system, where s is equals to sine theta, c is equals to cos theta, and we can write these guys as your transformation matrix. So this is a transformation matrix. If you don't ignore the axial displacement, if you ignore the thing, this would be your transformation matrix D for the rotation, right? Rotation from the this is from global to local. Is this is the transformations. So now the relation between k global and the local is given by, or you can write your transpose outside also, T transpose k local coordinate system times T, which is the same thing as your uh, thing for beam element, for pure beam element, that means there is no axial displacement, that is no axial displacement, your k global would take something like EI by L cube 12 s square minus 12 sc minus 6 ls minus 12 s square 12 sc minus 6 ls 12 c square 6 lc 12 sc minus 12 c square 6 lc 4 l square 6 ls minus 6 lc 2 l square 12 s square minus 12 sc 6 ls 12c square minus 6lc and 4l square, and this being the symmetric. If I take this as the t and multiply with my k local, in the local coordinate system we already know the k local which I used to write every time, so and multiply it in this manner, you'll end up with this one. So we'll use this kind of a thing for the subsequent stuff. So either so this part is also useful when I'm solving my subsequent problem. So this will be the last problem I'll be dealing it on the beams and bars today. So let me show the problem. Before that, let me stop here and ask if you guys have any questions here. So I don't know, for some reason it did not come. So let me copy it again. Okay, I couldn't copy it. Let me just draw the thing, the problem for you. So I have a point load acting at one point, and at another point I have an elastic support and an inclined beam with a pin boundary condition at this place and a distributed load at this place q, is which is a constant, that is a UDL, uniformly distributed loads. This is the problem we want to solve. So now here, what would be the best discretization that one can use to solve it in the finite element solution? So let us think about the mesh. In order to think about the mesh, the natural thing which I can easily do would be, this is the first element, the second element, this is the third element, this would be the fourth element. So element 1, element 2, element 3, and element 4. So the degrees of freedom. The degrees of freedom, since this component has a component that is acting vertical and a component acting in the horizontal direction, so this also has a pull, and we are not ignoring axial displacement. So that means these things behaves both as a bars and beams. So that means let me write the nodes first. The nodes are node 1, node 2, node 3, node 4, and node 5. So the connectivity table is, so for the element 1, element 2, element 3, element 4, the node 1 is, so for the element I and j is 1 and 2, this is 2 and 3, this is 3 and 4, and this is 4 and 5. This is node 1, node 2, and this is element E. So this is the connectivity table. The degrees of freedom would be d1x, d1y, theta 1, d2x, d2y, theta 2, d3y, sorry, d3x, d3y, theta 3, d4x, d4y, and theta phi. Now, when I come to this point, I will write about, I have actually d phi x, which is this, d phi y is that, so d phi x, d phi y, and theta phi, sorry about this, is theta 4. But I don't like this one in the global coordinate system. These are in the global coordinate system. Instead, I prefer to write here in the local coordinate system, where in the local coordinate system, I would like to prefer so in that manner what I can write is I can impose my boundary condition much simply, because in this direction we have only this d phi x in the local coordinate system, and this is d phi y in the local coordinate system. X is x and y. If you look at it, it's a pin joint. So you can easily impose your y and x in the local coordinate system compared to uh, the global coordinate system. So I would prefer to write this one in the local coordinate system. So and later time I will go back and convert into the global coordinate system. So now that means our degrees of freedom would look like d1 to d3, d4, d5, d6, d7, d8. I'll still write this thing as d14 and d15. Okay, so even though I started with a local coordinate system here, which is nothing but d phi x local, d phi y local, and theta phi, which is local and global, would be the same, the rotation it displays. So this is the degrees of freedom what I would like to do. So with this discretization, and I would try to develop my finite element method. So for that, I will show you the code, and so this is the problem FEM bar and beam example, which I've used at several places, this kind of problem. And so I will run through this you can find this example. This is the example taken from this reference, the steel structure design using FEM by Rolf Kidman, but you will not find the code. He might have just solved this problem in an example, but I have taken that example and tried to use it in terms of solving through finite element, because ultimately you want to learn the finite element with the numerical example and how to get through it. So I have already written the code, so I will go through it uh, in detail. So let us consider the inputs for this problem is, I'm considering my flexural rigidity as some 10 with some units, SI units, and axial rigidity as 1000. The length of the first piece of element, that is the L1, I consider L1 as this part. The element 1 length would be L1, the element 2 length would be L2, element 3 part would be L3, element part is 4, and where my discretization is, as I mentioned earlier, this piece of a length is L1, this piece of length is L2, this piece of length is L3, this piece of length is L4. So anyway, let's come back. So if you guys observe, this is the length of the beam 1, length of the beam 2, length of the beam 3, length of the beam 4, and the inclination of the beam 4, let us say, is 45 degrees. And let's the spring stiffness, this is the spring stiffness of this is Ks, because it is, this guy is supported not rigidly but on an elastic spring. So this is the elastic spring, or people call it as elastic foundation. So at this point is resting on an elastic foundation who has a stiffness of Ks, and we are taking that Ks to be equal to 1, and I'm also taking this force as inclined as at 45 degrees with F value equals to 10. So these are the force acting at the node 2, and the distributed load, this Q, I'm taking it as 100 Newton per meter. So this, you can play around with the numbers whatever you feel like. So now let us write the element stiffness matrix for the first element. The element stiffness of the first element consists of two things. So it consists of, since this is bar and beam element, so let me write down for you. So Ke, sorry, K of this combined element has entries of 6 cross 6. Why 6 cross 6? Because you have degrees of freedom, which is D1, D2, D3, D4, D5, D6. Similarly, D1, D2, D3, D4, D5, D6. You see that these D1, D4 are axial displacements. So these comes from the element stiffness matrix for a bar. We know for element stiffness for a bar is given by EA by L, 1 minus 1 minus 1, 1 is the element stiffness for a bar, which we derived previously. So that is with respect to the degrees of freedom of, for in our case, this is D1, D4, D1, D4. Similarly, for a beam, which we often write, six L, so Let me just finish it. This would be 4L square minus 6L to L square. This is 12 and this is minus 6L. This is 4L square. So this is for the beam, so which we have already seen. So now this is, we know this is with respect to the degrees of freedom, which is D2, D3, D5, D6, D3, D4, D5, D6. Now I have to assemble this onto this place. So what I do, I take this and assemble it over here. In that case, this will become, this is EA by L minus EA by L. This is minus EA by L. That is EA by L. Coming from this, D1 D1 entry goes here, D1 D4 entry goes here, D4 D1 entry yeah, D4 D1 entry goes here, D4 D4 entry goes here. Similarly, the D2 D3 is, I made a mistake. So D1 D3 D4 D3 D2 D3. Sorry, this is a wrong list. This is D2 D3. D4 is axial, so D5 D6. So these entries will come and sit here. So this would be E with the 12. This is 6LEI by L cube. Similarly, minus 12EI by L cube. 6LEI by L cube, and so on and so forth if you keep assembling it. That's the thing which I'll show in the MATLAB here. So this first, if we want to know what is the anyway, for the local coordinate system, I'll show what is the local coordinate system. So for the bar and beam would be this one coming from D1 D4 D4 41 and D44. BR means the stiffness coming from the bar. KBM is the stiffness coming from the beam element. So what we have done is I've assembled the same thing in this point of thing, and I have developed the KBB in terms of local coordinate system. The local coordinate system would be something like this. So if a beam and bar is there in something like this direction, this is the local coordinate system. In the local coordinate system, this is d local 1 by d local 1x. This is d local, see, this is transverse and this is longitudinal, 2y d local 2x. The rotations would be same irrespective of where you are measuring from, because it's an xy plane. So this is theta 1, this is 2. So that is what I'm doing in terms of a local coordinate system. So I'm assembling in the local coordinate system. Now in our case, which would be for the first beam, the inclination between the local coordinate system and global coordinate system is 0, so I don't have to worry about it. It will be the same for the second is also same, third is also same. For the fourth one, the angle is minus 45 degrees because this is the angle from between the global and the local coordinate system. Okay, so if you have any questions at this point of time, I will try to stop and check if you are understanding the things. Okay, I will not use yellow color. I1 and 3 D1 D1 such a kind of things. Anyway, let's come back to the code. So this is our KBB in the local coordinate system, and so if I come here, so my see what I need to give for K bar and beam. Let me split the windows so that you can see the things much elegantly, left and right. So this is the function. In the function, you need to give axial rigidity, you need to give flexural rigidity, the length of the beam, and theta in terms of radius, how it has inclined with respect to how the local is inclined with respect to the global coordinate system. So these are the things that has to be given into the consideration. So for that, for the first beam, you have seen that for the first beam, the axial rigidity is EA, the flexural rigidity is EI, the length of the first beam is L1, and it has inclined at a 0 degrees. So this is similarly for the second one. Again, you have EA axial rigidity, EI for the thing. Length is L2. Length is L2, and it has inclined at 0 degrees with respect to horizontal. Similarly, the third beam, which is this part of it, the third beam, it is also EA, EI, and with respect to local and global coordinates are matching with each other. However, only the last one, the fourth one, has some theta which is different from 0, which is nothing but minus 45 degrees. So for the fourth one, EA, EI, length of the 4, and theta in terms of radius, which is in minus 45 degrees, inclination of the fourth beam with respect to the thing. Now, we have element stiffness matrix coming from the first element, second element, third element, fourth element. And the spring stiffness is simply Ks, which is the K is also coming, and we need to see that where does the spring stiffness would affect in general. So let us see. So the spring stiffness would affect in this place D8 because it is the vertical thing that is stiffening it. So, and it would constrain the y direction, and hence the stiffness entry would come somewhere in D88, which we will show it in a couple of minutes. So that means we have stiffness of element stiffness matrix for the element 1, element 2, element 3, element 4, and for the spring, what is the stiffness we all have in our matrix format. So now, similarly, let us see the force vectors. Okay, so but this is in the global coordinates. Let us see how the global is calculated. The global is calculated based on, just now I've showed that it is nothing but, let us see the previous section. So I showed that it is K global is nothing but T transpose K local times T, and T is the transformation matrix which is given in this form. So I used the same thing here. So to find the transformation matrix, the transformation matrix is the same thing which I have used, C minus S. Here, since I used these things because it has both axial as well as transverse displacement which are under consideration. So my T is below instead of this one. This I would have used if my axial displacements are ignored. Here I have to use this because my axial displacements are not ignored. Okay, so I use this as the transformation matrix. Using this transformation matrix, if I already know the local stiffness matrix for the of the bar and beam, I mean T transpose K local times T will give me K global for the bar and beam. So this is my KGBB, which is nothing but bar and beam global stiffness matrix. So no matter whatever is theta, theta will give us the transformation T, and with respect to T transpose KBB, K local times T would give us global stiffness matrix. So at this place, so inside every global, what we initially did was we computed local and then converted into global with respect to the theta that is inclined. So that's how we obtain all the stiffness in terms of global degrees of problem without even bothering to even if it is inclined in this local direction, we have even converted that stiffness into the global stiffness. So next, similarly, we need to find our force vectors. The force things consist of the following. So it's very similar to this. We have an axial force NA, NB, and a shear force or the point loads PA, VB, MA, MB. So same thing I'm using here, or I might have called as VA. So NA, VA, MA, the nodal forces similarly at B, and then if you have an axial distributed load which is P and transverse distributed load Q, the length and its rotation is the thing that will be requiring it. So when we'll go there and see how, one thing we need to remember is, I'll go back here. This is how the K would vary. However, your F global F global is equals to T transpose times F local. This is the local transformation for the things, and D global is equals to T times T local. So we use this kind of a thing to so we use the same thing to convert back and forth our these things. So the force vector is calculated into T transpose times F in the local coordinate system, and once that is, if you know how the local has to be computed, for that what we'll do, we'll open how to compute the local things. In the local, we know that one comes from the if you look at it, so F local comes from NA, VA or PA, MA, NB, VB, and MB. So these two are axial degrees of freedom. These are coming from the beam. So these two entries I bring from the bar. So I get NA and B. Based on that, I get my F bar local, and similarly I get F beam local, and for the bar and beam I need to arrange it as first one is the bar, next two thing is coming from the B, which is this is NA, this is VA, there are 1 and 2, that is VA and MA, then this is NB, and this is 3 and 4 is nothing but VA and VB and MB. So I have arranged it in this thing, and then if there is transformation, this is the local thing, and from the local thing I can get the global F global by transposing it, and then I'm done with the transformation. So I'll go back to the place. So for the first element, let us see the first element. The first element, I'm not taking any forces. So the first element is, there are no forces acting on it. The second element will take the horizontal, as well as the vertical component of this F kind of y and fx that is acting at this will be taken by the second element at the node 2. First element I keep it free. So that's the reason I have NA, VA, MA, MB all are 0 for the things. With the element 1 it has oriented at a 0 degrees. There are no uniformly distributed axial loads, there are no uniformly distributed transverse loads, so everything is 0, and this would be my force on the element 1. Similarly, on the force on the element 2 consists of this thing, which is like in the x and y direction. I have actually given it in this thing, and then everything else is equals to 0, and then Fe3 global, again the third element is again this one is there is no forces. This spring will add to the stiffness, it will not add to the forces. So I will change my stiffness at a later point when I come to that. So that's the reason this is the third element is not loaded. So it is again all 0 is the third thing. Whereas the fourth one has a transverse loading. That means this load is acting in the transverse direction with a uniform load, which is equal to Q, and that magnitude has been given. We know that we have already computed the consistent loading. The consistent loading we have taken it as it's a consistent loading which we have taken it as WL by 2. WL by 2. This one is WL square by WL square by 12 and WL square by 12. These two are equivalent loading, which we'll do it in this thing. So let us just check that one. So this is coming for the force for the bar and beam. When we look into the local coordinate system, then we have this thing, force coming from the beam. It has two things, one coming from the concentrated loads, one coming from the distributed loads. The one coming from the distributed load, if I open it, it will be the WL by 2, WL square by 12, WL by 2 and WL square by 12, as we have seen in the previous thing. And then which I go back and I assemble it in the thing, and then finally I compute my forces on all these things. Now for each and every element, so what I obtained is, for each and every element, 4 parts of it, K element 1, D element 1, F element 1, like that I have obtained for the second element, for the third and fourth similarly. But I'm not just interested in obtaining just the element stiffness matrices. I have obtained each and every 4 parts of it, this one. But I'm not just interested in this. I want to assemble my K global by putting it into the thing. I want the assembly of the stiffness matrix, which is nothing but K global D global of F global. Okay. So why I need that? Because this is only for each and every element of individual elements. I want to do this. It would look something like this when I assemble it. So let me show you. When I do the assembly of this thing, the first element stiffness matrix would sit here, the second element stiffness matrix would sit here, the third element stiffness matrix would sit here, the fourth element stiffness matrix would sit here. So anyway, I will show you through the code how it has to be done. So let us look at here. So the first element degrees of freedom are 1, 2, 3, 4, 5, 6. So I'm doing the assembly here. The K global has 1 is to 6 to 1 is to 6 is coming from the element stiffness matrix of the first one. So initially I set the K global to 0. So every element entries are 0. And I have 15 degrees of freedom because I have already mentioned it. The last degree of freedom runs through 15. So K global is a 15 cross 15 thing. Now the first element has only contribution from 1 to 6, so it comes and sits here. Now the second element has 4, 5, 6, 7, 8, 9 degrees of freedom coming. So 4 through 9, whatever is already there, over that you will add the KE2. That's the reason this line is quite important. You should not ignore the first part of it. However, even though if they are zeros, so the second element sit here in this place. Similarly, the third element stiffness runs through 7, 8, 9, 10, 11, 12. So 7 to 12, 7 to 12 in columns are whatever is there to that already added KE3, which is coming from the third element. The fourth element is the thing. Okay. Now, once in a while, I try to put a rank here. The rank is, I just want to show that if you try to invert this, the K global is 0, which I've been always telling it for quite a while. So if an element, if a matrix is not invertible, it has rank deficiency. Right, so it should rank, if you want to try to see it, it may give not 15. If it is rank is 15, then that means you can invert this one. So when I run, you can just have a look at it. But now I just want to show that for some purpose I kept rank here to just to display it. Now let me just adjust for this spring stiffness. I know that existence of this spring is to stiffen this 8th position, right? To avoid this thing. So the stiffness Ks of the spring would come and hit at D8 and D8. So at the K global 8 and 8, whatever is there to that, your spring stiffness will be added. Okay. So now if I take the rank, because this is one kind of constraint. So rank will increase from here to here by 1.1. Now similarly I assemble, this is the assembly of the stiffness matrix. Similarly, I do the assembly of the force vector. By the same principles, the forces on the first one are depending upon 1, 2, 3, 4, 5, 6. So 1 through 6 global is coming from FE1, and 2 to 9 is, oh, sorry, 4, 5, 6, 7, 8, 9. 4 through 9 is coming from second element. 7, 8, 9, 10, 11, 12 is coming from the third element. So 7 to 12 is coming from third element, and I already converted into the global through the transformation, so I'm not worried about it of the local things. So I'm just worried about in the global thing, which is 10, 11, 12, 13, 14, 15 is coming from the fourth element. 10 through 15 is, and you have to add it to the previous thing. Now, this is your assembly. So what I did here is successfully through my program, I completed my K global. I have done this part, I have done this part, and I have also considered elastic foundation or elastic spring. So I even considered the part of elastic foundation. So one constraint is also already been added, but still this is not invertible. If you try to take the rank, you still see that it is rank deficient. Why? Because the structure, without putting a kinematic boundary condition, it would kind of not stable. So rigid body displacement comes into the existence, and a finite element cannot solve uniquely the rigid body displacement because there are infinitely available rigid body displacements. So for that you need to kinematically constrain that so that all the rigid body things are constrained. So let us see in the given problem what are the things that has been constrained. So here we can see that D1 is constrained, D1 is constrained, D2 is constrained because there is no x displacement, y displacement, and theta displacement. D3 is constrained. Similarly, there are no other things here. Now if you come to here, you have x kind of displaced in the local coordinate system and also y displaced in the local coordinate system. So in the local, these two are constrained. However, since this is a pin, theta is not restricted. These are converted. So we will anyway, we have a relation between local to global transformation. That means somehow these are also some way kind of constrained in some manner, not the theta phi. So there are 5 things that are kind of constrained. So those things are 1, 2, 3, 13, and 14. Since these two are constrained, one can show that when I apply the rotation matrix, D13, D14 will also come in the global, will also come to the 0 because these things into the things. So the fixed degrees of freedom are 1, 2, 3, and 13 and 14. So if I have to obtain KUU, which I used to do it in the thing, so let me write it. My D knowns are D1, D2, D3, D13, and D14. And D unknowns are D1, sorry, D4, D5, D6, D7, D8, D9, D10, D11, D12, and D15. 13, 14 are already covered here. So these are D unknowns. So if I have to obtain KUU from the KG, if I have to obtain KUU, what I need to do is I need to shut off the case rows and case columns. So that's what I'll do here. From the fixed total degrees of freedom, which is nothing but 1, 2, 5. If I remove my fixed degree of freedom, the reduced degrees of freedom is nothing but, which is like 4, 5, 6, 7, 8, 9, 10, 11, 12, and 15. So this reduced degrees of freedom is nothing but the set difference between all minus the fixed. Then KUU is nothing but from the K global, I only ask my reduced degrees of freedom and reduced degrees of freedom, directly I'll get KUU. Similarly, my FU is from the global, I ask only my reduced degrees of freedom, this is there. Similarly, all such kind of things. Now, as I've said earlier, so kg is nothing but, this is kg, right? Kg is nothing but KUU KUK K KU K KK, right? This is my K global, and we know that K this is K global, D global is equals to F global. So this can be written as D unknowns, D knowns, F U F K. This is this part of it. So anyway, this one because all are zeros, because all the so this is equals to 0, this is equals to 0, this is equals to 0, these two are equals to 0. That means even when I multiply with the transformation, I get these two also equals to 0. So I know that D1 through D1, D2, D3, D13, D15, D13 and D14 are zeros. So this I can directly write that this equation is nothing but KUU into DU is equals to FU, or my unknown degrees of freedom is nothing but KUU inverse of FU. So that's what I've been doing here. So my KUU, I got it, my FU is there. So before I do the inverse, I ask for the rank. Since this structure is statically stable, because all the rigid body displacements are kind of removed, KUU is non-singular. That is, it will not have rank deficiency. So if you try to see the rank, it would be the same as the order of the matrix KUU. So here you will not see the rank deficiency. When I run, you can see it. Now there I'm using it in this manner. This is nothing but KU inverse times that. This only does LU decomposition kind of a form. So KU inverse time FU is an alternate way of writing it in MATLAB so that LU decomposition can be used. So anyway, you are computing your UU. Once you know UU, then you use the second equation. The second equation says that KU times DU is equals to FK. So anyway, this from the first equation you solve this one. So you know this, you multiply this, you get your reaction forces. So obtain the reaction forces. Fr is equals to, I call it as Pu instead of Ku. So KKU times UU will give you your things. In this manner, you solve this entire problem. So let me run through it quickly. And so initially when you saw that the rank at this place, when I assembled entire thing, it is not rank is 15, rank is 12. That is what it is showing. So it is not 15, so it is not invertible. When I applied the elastic foundation constraint, the rank has increased as by 1, because one rigid body displacement is constrained. So it becomes 13. Now I have 15 degrees of freedom. Out of 15 degrees of freedom, I have constraint 1, 2, 3, 4, 5. So if I remove 5, the rank of the matrix should be 10. So that's the reason if I seek the rank again at this place, the rank comes out to be 10. So that means KUU is 10 by 10 and rank is also 10. That means KUU is invertible. That is, I can use inverse KUU times FU, or this LU decomposition form can be done. This multiplication, this kind of thing would yield me a valid UU. So that's the reason this writing an equation is valid, and hence I obtain my displacement accurately. And once you know the unknown degrees of freedom, I can KU. So these are the things for the given things. So if you want a full thing, so what you need to do is just copy this. I'm just in the folder, so just run it. So your reduced degrees of freedom are 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Fixed degrees of freedom are this one. Your unknown degrees of freedoms are something like this, and your reaction forces are FR are given by these things. So the reaction forces are nothing but this is the axial displacement at the node 1. This is transverse reaction at the node 1. This is the moment at the node 1, and these are the kind of axial as well as transverse forces at the node 5. So you have reaction forces coming at this. So first one is the horizontal, next one is the vertical, next one is the movement. Similarly, you have axial, this and this reaction forces from this pin joint. So all the phi are obtained as through FR. So this is your a small program to see what I have been telling it over a lot of classes. This covers a basic finite element in most easiest fashion. You can write this code in multiple ways, but I have written it in a very layman-ish form so that everything is apparent as we do it in a class. But generally finite element codes are not written in this lame fashion. This is written in this lame fashion only for a reason that it is exactly representing how I teach in the class. But when you write an efficient programs just like a commercial software, the assembly and other things are done in much more automized fashion rather than this. Even development of elements matrix is not in this manner. You will try to do a template-ish manner in a different thing. Anyway, we'll come to that in the subsequent times later. If I have some more time, I'll try to show some more finite element parts of it. So with this, my chapter on the finite element on trusses, bars and beams are completed, and I have also demonstrated using a